So, when looking at basic sort of calculus-based physics, calculus-based mechanics, a really important concept to look at is simple harmonic motion. And harmonic motion is based upon the idea of oscillations. So this is just talking about oscillations. Sorry for my handwriting, but because of that, it's something that I want to just introduce in this first lecture on simple harmonic motion. We're just going to look at what it is and then how we can define it using calculus. And then we'll look at other problems, etc. in future videos. So simple harmonic motion is based around oscillations. And as oscillations is basically a fancy way of saying back and forth, going back and forth. And a great example of something that oscillates would be a spring. So imagine that you have a spring that, let's say, it abides by Hooke's law. That's my drawing of a spring. And we put some pole on it. Let's say this is the normal equilibrium length right here. And so we've pulled it this much. Oops. We'll call this a distance of x. The fact is when you pull it this much and you release, this, if we sort of track this red point right here, we'll see that this red point starts here, it goes up, it goes down, goes up, it goes down. And so if this is, for example, time, and this is the position, we're going to see it go up and down and up and down. And so, funnily enough, I'm going to prove this by the end of the video, but what we see is that this sort of graph moves in the form of a cosine wave. And this sort of makes sense. If you remember back to your trig and pre-calc classes, you remember that cosine essentially just looks like a up and down graph, and centered around 0 with an amplitude of 1 and 1. And what you also might remember is that you can sort of influence this cosine function by adding variables around it. So for example, if you were to write cosine t, it might have a period of 1, and period is just the length or the amount of time it takes to do one full, to go right back to the point it was started at. However, if you add a coefficient in front of it, let's say you did cosine 2t, this decreases that period. And so by adjusting variables, the variables in this case, this is omega and this variable a, you can adjust how large these waves are going to be, and you can adjust the speed at which these waves come. And so the fact is that simple harmonic motion is defined by this, at least in one dimension. If we look at this spring, and we look at how it's moving without, including air resistance, friction, etc., then we can really say it's defined by the equation a cosine omega t. That's how it's going to move. And as I said, I'll prove that to you by the end of the video. And so let's just start to make that proof, to make the connection between a spring that follows Hooke's law. Remember, springs following Hooke's law, and to make that connection between that Hooke's law and this equation, we'll need to take some derivatives. If we take the first derivative of this dx dt, we're going to get velocity, and that's going to get us negative a omega sine omega t. Hopefully I didn't make any mistakes there. And then if we take the derivative again, and this is going to give us the acceleration at any given point in time t, we're going to get negative a omega squared cosine omega t. And so if we look at this, once again, we'll see that the x here, or really that this second derivative is sort of based on x. And to rewrite that, to really illustrate that, drive that point home, I'll write it again, sort of in a different way. And so here you can see this based on this equation, we have this equation, we know it's true at the very beginning, we created it, we can really plug that in here. And based on that information, we can say that the acceleration is equal to negative omega squared times x, because that's what this a cosine omega t is equal to. And this right here is the definition of simple harmonic motion. Any sort of item that moves in this sort of fashion, actually, sorry, before we get there, actually, we'll take one more step. Remember, this omega is a constant, and so we can just call this constant c. If we say omega squared equals c, then we can say negative cx. And so here, right here, this is the equation of simple harmonic motion. Any sort of item that follows this acceleration, or follows a acceleration equation that looks like this, where c can literally be any number, will move with simple harmonic motion, just in a back and forth oscillating sort of motion. And so now let's connect this to a spring. If we have a spring, the force at any given point that you pull it back is negative kx, and this equals ma. And then if you want to find the acceleration thus of a spring at any given point that you've pulled it back, it's kx over m. And this can be written as negative k over m. Remember that k is the spring constant, m is a mass. M is the mass, which is also a constant. So really, this entire thing, it's just a number. So we can replace that with c. If we replace that with c, we get, oops, this should not be a k. We get negative kx. The acceleration of a spring that follows Hooke's law is going to be negative kx at any given point. This is as I said before, it's exactly what we have here, which is exactly the definition of simple harmonic motion. There you have your proof that a spring that abides by Hooke's law is going to move in a graph that's defined by this equation up here, x equals a cosine omega t, or sometimes you'll have a sine omega t, but really it can be written in either form. So with that, I'm going to leave you there, and we're going to talk a bit more about this in the future lecture.